So the statement of the theorem is a subset S considering of the vectors x1, x2, so on up to xn of a vector space Vf is linearly dependent if and only if some, or say at least one vector of S is or can be expressed as a linear combination of remaining vectors in S. So the statement says that if we consider a subset of a vector space Vf and we want to know whether that is linearly dependent or independent, how do we do that? It is possible if and only if we would be able to find some of the vector of that subset which is expressible as a linear combination of the remaining vectors in S. Also, since the theorem's statement consists of this if and only if, it means we have to prove the converse part also. That means the converse part also holds. What's that? It is like if we are able to find out a vector in a subset S which is a linear combination of remaining vectors in S, that means the subset is surely linearly dependent. So now let's look at the proof of this theorem. So first, let us suppose that the subset S of vector space Vf is linearly dependent. So first of all, we are assuming that the subset that we have considered is linearly dependent. So by definition of this linearly dependent, what does this imply? This implies that there exist scalars, say alpha 1, alpha 2, so on up to alpha n, belonging to that field on which our vector space is defined. So there exist scalars alpha 1, alpha 2, so on up to alpha n belonging to F, not all 0, such that this equation holds. That is alpha 1 x1 plus alpha 2 x2 plus so on up to alpha n xn equals 0 when we have considered the scalars such that they are not all 0. That means we have at least one scalar which is non-zero, right? So consider this as first equation. Next, now since we know that all these alpha i's are not 0, or I can say alpha i's are not all 0, what is I is 1 to so on up to n, this means we can take some particular value of alpha I. So in particular, let alpha k is not equal to 0 for some k, right? We have just considered a particular case of that. Now from 1, what do we have? We would have another equation, this one. So since we have considered some alpha k, so this alpha k is not 0, that means the term consisting of alpha k must be somewhere here in between, right? So which is this I have written here. So what my equation has become right now is alpha 1 x1 plus alpha 2 x2 plus so on up to plus alpha k minus 1 xk minus 1 plus alpha k xk. This is the term containing this alpha k. So next is plus alpha k plus 1 xk plus 1 plus so on up to alpha n xn equals 0. This is nothing, this is just this equation, and I have just written some of the elements that are in between this equation, so don't get confused. Now what my next step is going to be that I'm going to keep this alpha k xk here and shifting all the remaining terms to the right hand side. Let's see what happens. So here the equation becomes alpha k xk equals minus of alpha 1 x1 minus alpha 2 x2 and so on up to. So this minus is because we have shifted the terms from LHS or left hand side to right hand side. So next we are going to pre-multiply both the sides of this equation by alpha k's inverse. So what do we get? So here in this expression, when we pre-multiply it by alpha k inverse, we're gonna get alpha k inverse alpha k xk, where alpha k inverse alpha k when multiplied will give us identity, which multiplied by xk will give us nothing but xk. And on the right hand side we have just written this alpha k inverse outside and rest of the terms inside the bracket. So now we clearly know that we can distribute this alpha k inverse with each of these terms. So what are we going to get? So it is this expression. So alpha k inverse alpha 1 and along with the negative sign with x1, this thing, and so on. So now point to be noted is that this equation or this thing, you can clearly see this is a scalar. A scalar times scalar is a scalar. This is again a scalar, this is again a scalar, this is scalar, scalar. So now, and the other things with these scalars are x1, x2, so on up to xn. So this means some xk, which is an element of S, we have assumed it earlier, has been expressed as a linear combination of x1, x2, so on up to xn, which are nothing but remaining elements of S. What does this mean? This means what we were to prove is done. So this was the trick part. Now let's see the converse part. So conversely, let us suppose that some element of S, say xk, can be expressed as a linear combination of remaining vectors, say x1, x2, so on up to xk minus 1, xk plus 1, so on up to xn. So we have excluded xk from here because it has to be expressed as a combination of remaining vectors. Next, that is, what does this mean? This means xk equals beta 1 x1 plus beta 2 x2 plus so on up to plus beta k minus 1 xk minus 1 plus beta k plus 1 xk plus 1 plus so on up to beta n xn. Now we're going to shift this xk to the right hand side. What are we going to get? See, one thing to be noted that these beta i's belong to F, that field. Now when we shift xk to the other side, we're gonna get minus 1 xk here, right? And the remaining terms are as it is, and this thing is going to be equal to 0. Next, what does this imply? Clearly on observing this, we're gonna get there exist scalars beta 1, beta 2, so on up to this. Not all 0. Why not all 0? Because there is at least a scalar, this beta k. See, this is beta k, which is equal to minus 1 but not equal to 0. So there exists a non-zero scalar, at least one we need. So such that the equation this is 0, that means this equation was 0. So this is what? This is nothing but definition of linearly dependence. So it means this set that we considered earlier is linearly dependent subset of V. Now we have some points that we should discuss. So those are, okay, so the first point that I want to discuss with you is this one. Okay, so there's some points. So okay, so I've written, don't confuse remaining with preceding in the statement. So clearly if you read the theorem, you see I have used the word remaining, not preceding. So we also have a theorem with this word preceding, but the theorem that I've covered in this video is not the one with the preceding, but it's remaining. So remember that. Next, second point, does alpha k inverse exist? We remember we used this in the video, but does it exist? Because why I have raised this question is because we haven't checked its existence, we've just directly used it. So if you know the answer of this question, please let me know in the comment section. Thank you.